And welcome back. In this video we're going to look at the common base amplifier configuration. This is not a commonly encountered configuration as the input impedance is very low, used more in RF amplifiers where it's common to find low impedances. Did I not say that the Experimenters Kit is now sponsored by PCBWay? The one-stop shop for all your PCB needs, 3D printing, assembly and many more. Go visit their website and have a look today. This is the common base amplifier configuration where the base is said to be common to both the input and the output. This circuit gives less than unity current gain but can provide quite high voltage gains. So just to give a quick idea why the current gain is below unity, e.g. less than 1, let's have a quick look at the circuit. Let's say the circuit has 1 milliamp flowing through the emitter resistor. This 1 milliamp is made up of the currents flowing through the collector and the currents flowing into the base. So thinking about this, the current flowing into collector must be less than the current flowing into the emitter by the amount flowing into the base. So the current gain could never reach unity, i.e. 1. But as we'll see later, the voltage gain can be quite high. So let's start with the design. First we'll decide on the emitter value resistor. So let's make the emitter voltage equal to 1 volt with a current flowing through the emitter resistor of 1 milliamp. This makes the maths easy, so R4 equals 1 volt divided by 1 milliamp equals 1k. We want the base to be 1 VBE drop, or base emitter voltage drop, above the emitter. So we'll look at the data sheet and see what the common value is for this transistor, which is about sort of 580 to 700. But we'll go for around the 660 as that's a sort of typical value. And that's what we use in this design. So let's aim for a base voltage of 1.6 volts. And again, to make life easier, let's make the current flowing down the base bias resistor chain 1 milliamp. So then R2 equals 1.6 volt divided by 1 milliamp, which equals 1.6k. But I have a 1k resistor and a 510 ohm resistor in my kit, so let's just put them in series for the 1k 5.1. It's close to 1.6k, it won't make a lot of difference. Now we will forget the base current as it's quite small. So I'll select the value for R1 as 9 minus 1.5 volts divided by 1 milliamp. This gives a resistor value of 7k5, but that's not a standard value. So I'll use 6k8 as it's close enough for my experiment. It's only setting the DC conditions, so it will not affect the circuit performance too much. I will then decouple this with a 10 microfarad capacitor so as to reduce noise from the supply, affecting the base current and then affecting the output. To finish off the DC conditions for the circuit, we need to pick a value for R3, the collector load. Based on the fact it would be nice to have the output to have maximum headroom, we would aim to have the collector voltage about half the supply voltage, e.g. 4.5 volts. So again, R3 equals 4.5 divided by 1 milliamp equals 4k7. So we'll put that in. And just to round off the AC decoupling for the input and the output, we'll use 4 mic 7s capacitors, or 4.7 microfarad capacitors, as I've used them before and they're already on my little PCBs. So we'll stick with them. They'll affect the bandwidth a bit, the low frequency end, but just for the experiment I'm not really worried about that. Now we have the circuit design, let's build the kit with a little background music. Here we'll check the DC conditions on the circuit. As we can see, the supply is set to 9 volts. The voltage on the emitter, which you wanted 1 volt, is 0.993, so close enough, even though we've used, standard values and not the ones we calculated. The voltage on the collector, I was aiming for 4.5, we got 4.36, so close enough. It's about mid-range of 9 volts, so kind of maximum swing possible. It's not the maximum because obviously the emitter's capped at 1 volt, but it will give us a reasonable swing. And then a quick look at the base voltage, and that's 1.63, close to what we designed. Next thing to do is have a look at what the AC signal does and talk a bit more about the circuit. Right, let's have a look at the AC characteristics. I have a signal coming in from my oscillator, set to 10 kilohertz, ground going to 0 volts. We have the yellow trace on the input, the blue trace on the output, and as you can see up there, the input is smaller than the output, so we have gain. So let's measure the input voltage. So let it settle down. Ground lead's fallen off. Right, so we have, as near as damn it, 10 millivolts going to the input, and we have 1.6 volts on the output. And the trace on the screen from the oscilloscope is using the Handtech PC control of the scope, so it's not just a printer. I can move things around just to show you that it's not just a static photograph. It's got a lot of averaging on to reduce the noise, as my bench is a bit noisy. So there you have it, the AC characteristics, or gain anyway, of this circuit. And now we'll go back and see if we can calculate it to see how close it is to the calculated values. Now we need to talk about the AC characteristics of the amplifier, having just seen what we measured at 10 kilohertz. The frequency was set at 10 kilohertz as opposed to like the normal 1K, as the impedance, input impedance, is very low, and it's a small capacitor, so they together could be acting as a high pass filter and lowering the gain. So I've upped it to 10 kilohertz. We should be well in away from the slope of that RC filter. So what is the gain, and is it the same as we measured it? The gain of a common base amplifier is plus RC divided by R-E. The plus sign is showing that it's non-inverting, i.e. the output is in phase with the input. Now R-E is called, or often called, the intrinsic emitter resistance, but it's not in fact a resistance at all. It is the inverse transconductance, where R-E equals 1 over GM, i.e. it's a transfer quality, or the dimensions volts divided by amps. So now we know that, we're good to go. Whether we understand it or not, I don't know. First of all, RE, as we just said, it's the transfer characteristics, and it tends to be taken as either 25 to 26 millivolts divided by the emitter current. So we're using 1 milliamp, so we'll bring that up. So 26 millivolts divided by 1 milliamp, and we can all guess what that's going to come out as. 26 ohms. And we've said that the gain is equal to RC, which in this case is the resistor, the collector load, which is this one, and this value. So we can bring that in, and there's our gain. 4.7k divided by 26 should give us a gain of plus 180. And I think we found, measuring at 10k, that the gain was 160. So quite close, but you know, in the right ballpark. And again, you know, we're just taking this as being 26 millivolts, 25 millivolts. It might vary from transistor to transistor. So, you know, the calculations may be slightly out. So, what we said about the input impedance. Well, there's the input impedance, and that's what, you know, it's that capacitor is looking at the input impedance here, which we would think would be 1k. But in fact, it's the input impedance is the emitter resistor in parallel with R-E. So it gives us an input impedance of 1k in parallel with 26 ohms, which comes out as 25 ohms. So quite a low input impedance. If you wanted to match 50 ohms, if we doubled the current, then we could probably get away with making this 50 ohms or nearabouts, because we doubled the current, this would probably come out as 52. And what about the output impedance, you may ask? Well, the output impedance is simply this. So we add that over here. The output impedance equals RC, or R3 in our case. That's about as much as I'm going to tell you today about the common base amplifier. I hope you found it entertaining or interesting, and that one day you might find a need on how to use this. Especially if you're working in RF, it's quite common there. So if you enjoyed it, hit the subscribe button, click on the notification bell so you see more of my videos, and hit the like button. Only once, because if you hit it twice it's unliked. So 3 times maybe. And I'll catch you on the next one. Bye for now.